All right, so on Thursday, when we were playing with the pendulums and the springs, first, I think there was a group who varied the mass and measured the period, and you've got some very boring data right here, and we decided that mass does not affect the period. It was pretty much the same. Then there was another group that varied the height. Varying the height is also similar to doing what? To varying what? About the pendulum. The height and the length aren't the same. The length is the length of the string. The angle that you pull it back to, yeah. If you pull it back to a bigger angle, you're going to have a greater height. Okay, and then we did graph the period versus the length, and I really wanted you to see this increasing but changing type relationship there. The period was a function of the square root of the length. So the period is affected by the length. All right, so then at this point, I had drawn the pendulum. So let's put an angle in here, theta. And so in terms of the motion, just like the WebAssign question you were talking about, we were talking about the peg on the wheel and watching the shadow. If we were to watch the shadow of this pendulum, it starts, of course, down here, we pull it back. It would go from here to the middle and then swing up, and it swings back down. So the shadow would be moving back and forth on the floor like that, okay? So the amplitude would be this distance right here, which means it would be very similar to, isn't this L, the length of the cord? Wouldn't that be like this distance right here? If you have L and theta, can you find how far away or what the amplitude would be? That opposite side of the angle? Any ideas? Yeah, we can use the sine function. So the amplitude would be what? L sine theta? So the most important thing about this pendulum's motion is the fact that there's always a force trying to pull it back towards the center. So when the pendulum is up here, what forces are acting on the pendulum bob? Whoops, that was ugly. The pendulum bob when it's up there. When it's pulled back over here, what forces are acting on it? Definitely a gravitational force. Anything else? There would be a tension force acting on it. If you wanted to draw a really not pretty version of a Freebody diagram. Now this gravitational force right here, if you want to think about it in terms of this angle theta there, okay, then wouldn't this right here also be theta? Okay, so could we separate this gravitational force into a component that is opposing the tension? So the gravitational force that's opposing the tension, and a gravitational force that is pulling it down towards, so gravitational force that is perpendicular to the radius or to the length of the string. Separate it into its components, y and x. What would this perpendicular component be? Perpendicular to the length of the wire. It's opposite of theta, so how would we find that component? Do you remember? Yeah, it's a sine function too. So FG sine theta. That force right there that is pulling the pendulum back down towards the center, and you know, as it swings through the other side, what's going to happen to that gravitational component? Which way is it going to be pointing when it's over here? Back towards where? Where is it pointing towards all the time? The center or the equilibrium. This is called a restoring force. And a restoring force is what sets simple harmonic motion. It's needed for simple harmonic motion. simple harmonic motion. And that's really what sets apart just harmonic motion from periodic motion. Periodic motion is motion that happens over and over and over. So like the moon periodically orbits the earth, but there's no restoring force on it. There's no equilibrium position, so it's not harmonic. But a pendulum has a restoring force on it, so it is periodic and harmonic. So you have to have a restoring force. And a restoring force means that it's simple harmonic. All right, so this force right here would be a maximum when I pull it back to the maximum height. So let's see. If we have the maximum force and F equals ma, then that would be a maximum acceleration, right? And our maximum force when we pull it back to theta would be Fg sine theta. And let's see, what is A max for like this harmonic repetitive motion? It's not the centripetal, what we came up with. What do you think it is? It should be the amplitude. All right, so A omega squared is the acceleration. Very good. Now what is Fg? Fg is what? Mg. So that would be Mg sine theta. What did we just decide the amplitude of this thing would be? L sine theta. Very good. Times omega squared. Okay, what can I do here? Looks like I can divide by m on both sides. So did the mass change the pendulum? Holy cow. All right, what about theta? I got sine theta and sine theta. Did changing the angle change the period? This is where you say no. Okay. All right. So then we're left with G equals L omega squared. In terms for the pendulum, omega is G divided by L under the square root, and that's a great thing to hang on to. Y'all like boxes. I know that looks like an E. Let me make it look a little bit better. L, the length, so the acceleration due to gravity. The one thing I couldn't change in this classroom was the acceleration due to gravity, so we didn't get to experiment with that one. And then, how is period related to omega? Omega is 2 pi over the period. So could you say, therefore, the period is equal to 2 pi over omega? Oh, can I substitute my omega for this pendulum and have the period of the pendulum is 2 pi over the square root of G over length? But that's kind of ugly looking. So how about we make it 2 pi times the square root of L over G? And that is the period of a pendulum. Now a little P beside it stands for pendulum.